Hi everyone, this is Emrah Turgut. Today we will continue chapter 31. It's about radioactivity and nuclear physics. So in this chapter we will basically cover the properties of the nucleus, how they form, how they decay, what are the outputs, and somehow we measure the radiation and so on. So to define the nuclei, we define first number of protons. That defines the type of element. For example, for aluminum here we have 13 atomic numbers, and neutron number n, it's the number of neutrons. And normally we don't show the neutrons when we show the element. What we do is we show the mass, which is a mass number, which is the total number of nucleons, protons plus neutrons, and we put that on the left upper side. For the aluminum, for example, the total atomic number is 27. The mass number is 27. So the neutron number is 14. So we don't show it. We have neutron, 13 protons. So total makes 27 mass numbers. For example, for carbon, the atomic number is 6. It has 6 protons, but it can have different number of neutrons. So we call this isotopes. This is for the most common one is carbon 12, and then I think carbon 13. For hydrogen, as we have 1 proton, no neutron. When we have 1 neutron, it's a deuterium, and tritium when we have 2 neutrons. So this is again describing in words. So they're called isotopes. There are different isotopes. In this table, we show these isotopes and most common element. So for carbon, you see the 6, 12, and 13. For lithium, you see 2. So uranium, you can see these 2 ones. Okay, so how did now let's talk about the radioactivity. Because of the high atomic numbers, some elements decay. We will talk about that binding energy. Some elements in the nature, they are not they don't have a most stable nucleus, so they decay. So it has been discovered in end of 19th century, actually by H.A.H. Becquerel. So what he did is at that time we already discovered the photographic plates, like the what do you call it, films. So in his experiment, he put the radioactive material on this film in a dark room, and he waited for a while. And he observed these shapes, as it shows the shape of the rock, which has, I guess, uranium. Actually, you can watch this experiment on this YouTube video. So then this phenomenon is called radioactivity. At that time, it was not fully understood. Marie and Pierre Curie actually described this phenomena better, and they isolated two radioactive elements, polonium and radium. So they did a lot of research on this nuclear radioactivity. Okay, so in the radioactivity, there are more, but the most common particles are alpha, gamma, and beta. So in early experiments, people try to understand what's the output of these, the radioactivity, and here they have a source. It emits alpha, beta, and gamma particles, and under the magnetic field, you see this type of deflection. So if you don't have any deflection because of from the magnetic field, so what you can say the gamma is the photon, and if you use the right hand rule, you will find that the alpha is a positive particle with a positive charge, and beta has the negative charge. And then they also did experiment how these particles penetrate in different materials. For example, the alpha particles, they cannot penetrate. You can stop them in just with a piece of paper. Beta rays, they could penetrate about 3 millimeters in aluminum. For gamma rays, they can penetrate most of the material, and you need to have a kind of heavy metal to be able to stop it, and it has to be kind of thick. And then we learn later as we do the experiment, alpha rays are helium nuclei. So in the helium nuclei you have 2 proton and 2 neutron. It doesn't have an electron. So beta rays are electrons, and gamma rays are electromagnetic radiation, which means the photons and high energy photons. Of course, these protons and neutrons in the nuclei have some mass. So proton mass is this 1.67 and so on, 10 to minus 27 kilogram. Neutron mass is this, and you see slight difference. They are not identical. The size of the nucleus, it's because of the wave particle duality, the nucleus size is also not very solid, like it has some uncertainty, but it's about femtometer, and also depends on the atomic mass. So to be able to understand the relation, for example, location of the electron and the size of the proton, the electron is about rotating 10 to the minus 10 meters radius, and the nucleus is at the center, and its size is about femtometer, 10 to the minus 15. So for example, if the stadium were a hydrogen atom, the nucleus would be a garden pea at about a second base. So think about a nucleus here as a pea, and the electrons would fill the city was in. So the electrons are gonna be wavy particles around the city. So that's how big the atom and how small the nucleus. Now we'll talk about the energy of mass. So from the relativity, you don't need to know exactly this one. What you need to know is the stationary, the mass at rest has this energy, mc square. So it's just Einstein's famous formula. Then the masses of atoms are measured with the reference to the carbon 12 atom. So we made a kind of carbon as a reference. It has 6 proton and 6 nucleus, and we said 12 atomic mass, and we call it atomic mass unit. We describe this as a kind of reference, and one atomic mass is 1.6605 10 to minus 27. So this is in terms of energy, electron volt and centimeter square. C square. So if you look at the mass of the proton and neutron, you will see 167 to 167.4. 167 to 167.4. This is proton, and this is neutron. So you see that atomic unit mass is less than the mass of proton and neutron. So what it means is, although the carbon has 6 proton and 6 neutron, its nuclear mass is actually smaller than the total mass of protons and neutrons if you count them individually. So what we now come to point is, actually the atoms have less mass than what you can count when you weigh the individual protons and neutrons. So now we will come to this binding energy. Actually, this table shows the relation that it compares the masses of protons and neutrons and hydrogen atom, and this is about in terms of U, atomic mass unit, and in terms of mega electron volt C square. Okay, then as I said before, now the atom weighs less when you compare all the protons and neutrons it has, and this mass, where is that? And then but indeed it becomes as an energy, and it's a binding energy, we call it, to keep the nucleus stable. So if you think in terms of this is a kind of general physics rule, the matter always wants to go to the lower energy. So what happens is, when you have an atom it has less energy compared to all the individual protons and neutrons, so the atom is stable. So otherwise, if it has more energy, then it will not be stable, and all the protons and neutrons will be separated at some point of time. And we call this binding energy, and depending on the element, we see this chart. So every element has a different binding energy. So the higher the binding energy per nucleon, the more stable the nucleus. So as you see in the chart, the hydrogen and helium are not that stable, but as you go to heavier elements around iron and nickel, you see the most stable nucleus. And after that, if you go to heavier element, they become more the binding energy decreases. So what you see here, like the most stable elements in the universe is iron and nickel. And for example, the nucleus of many planets, stars, has iron core. And we have this magnetization also from these elements in the cores, at the cores of the planets and stars. Anyway, like in the natures, when you have some reaction, the heavier elements will decay to lighter element, like to iron, and the lighter elements will combine and become heavier until the iron. And for the light elements, usually we have same amount of protons and neutrons, but as we have a lot more and more protons around here, to be able to have a stable nuclei, the proton number of neutrons increases. It's not stable, it's not equal, it's not equal to the proton anymore. So because the Coulomb repulsion between protons becomes stronger, so to make it stable, number of neutrons increases. And we don't talk at this class, but there are forces between protons and neutrons to hold them together. So nuclear forces. So with that, the nuclei become stable when it has more neutron. Oh, actually, we talk about this strong nuclear force. It holds the nucleons together. So when they have a unstable decay, that causes weak nuclear force. And when we have this alpha, beta, and gamma particle emission, the total nucleon number must be conserved. Also, energy must be conserved. For example, when a nuclei with the atomic number Z, mass number A, when it goes into the alpha decay, it will lose 2 protons and 2 neutrons. So at the end, the new element has 2 less proton and 4 less atomic number. The atomic mass. When we have a beta decay, what we do is we create 1 more proton. Actually, the neutron becomes proton and electron, and we have this neutrino. It's another subatomic particle. Here, what you see is it's like doesn't have a charge. It's light. It travels very fast. And you don't have to think about this a lot, but what you need to know is in the beta decay, the proton undergoes the beta decay, and neutron becomes proton and electron. So here you conserve the charge, and at the end the atomic mass is conserved. It doesn't change, but the proton increases 1 by, number of neutrons drops 1 by as well, at the 1. So they are different. Okay, so for this is a electron beta decay. You have this positron decay. In this case, the proton turns into neutron plus positron. So positron is an antimatter of electron, which has the identical mass but opposite charge. So in another beta decay, which is an inverse beta decay, the atom can capture electron, nucleus can capture an electron. So here what you do is electron combines with the proton and becomes neutron. So proton, the atomic number drops 1 by, but atomic mass doesn't change. Beta decay, the atom, the nuclei just loses the energy. It doesn't lose any proton or neutron. So for example, this is one example for the radium decays to radon with an alpha decay. So 88 proton, it loses 2 protons and 2 neutrons. Then this is an alpha particle. Okay, this is alpha decay occurs when a strong nuclear force cannot hold a large nucleus together. So when we have an alpha decay, the nuclei loses a lot of energy because it loses a lot of mass. If you compare with the beta and gamma decays, it happens when you have a very large nucleus. So the strong force cannot hold it. And the sum of the masses to nucleus particle, this difference called disintegration energy. So alpha particle is stable. So this process, this disintegration is likely in the nature. So actually we use this as a smoke detector. For example, like in all the smoke detectors we have a radioactive material, and when we have a smoke, the alpha particles cannot, let's say, travel or penetrate. It's absorbed. Then we can measure, like we can say there's something blocking in front of the collector plate, so we can say there's a smoke. So this and here we had talked more about beta decay. So carbon, for example, becomes nitrogen. So I said the neutron becomes proton and electron. And this is about neutrinos. It's very light, it's very difficult to detect. Yeah. The beta decay, it doesn't have to only be electron, it can be also positron. So it's like an electron with a positive charge. So for example, here neon turns into fluorine, and the proton number, atomic number drops by 1, but the atomic mass doesn't change. And the nucleus can also capture electron, and which in this case the proton plus electron becomes neutron. Then gamma decay, it's about more details. Here then the carbon nucleus is in excited state. This is not electronic state. You can think as a nucleus states. It doesn't change. That's atomic number or atomic mass do not change, but it emits energy because it's a high energy state because of the decay. So this is a very actually nice graph to show how the decay happens from uranium to other elements. Actually, by the way, you can ask if the uranium is not stable, how it is formed at the first place. Actually, these heavy elements like uranium and all these radioactive elements are formed during some huge astronomical events like supernova explosion or some events in the stars or star explosion and so on. So you can, they can be a lot of energy. So in this process, some light elements like iron and so on, they can form these heavy elements because of the energy. So for example, uranium 280 to 380, so it can have alpha decay. So here in one, when you go left, you lose one atomic number, right? So the uranium, for example, in alpha decay, it loses 2 protons, and the left, the y-axis is the atomic mass, and the 1 unit is 4. So when you have an alpha decay, the proton number of protons drops by 2. Then the atomic mass drops by 4, and then the nucleus undergoes to the 2 beta decay and becomes uranium 234. This is more stable, and the news you usually hear about the enhancement of uranium and so on. Actually, this 238 is more efficient in, let's say, as a weapon, also in the radioactive fuel in the nuclear plants. Anyway, so then uranium goes to thorium, then alpha decay, and so on. You see also in the graph you see half-life times. So this radioactivity has some the lifetime. So in this amount of time, the element loses half of its mass. It undergoes to radioactive decay. So you see the uranium 238 is about 4 billion years. So actually the uranium 238 versus uranium 234 are used for geographical dating, for example on the rocks and etc. The most of the time we use carbon 13 and carbon 12 for biological samples like fossils, but for longer time scales we use uranium. Okay, this slide shows some fancy graphs about how these uranium decays with alpha particle and beta particles until the lead, and it shows this alpha, beta, and gamma particles, how you can stop and so on. So you can look at these slides, it's kind of interesting. Okay, when these radiations indeed are not very safe for us, let's assume for example for gamma rays, it can penetrate through your body. If it penetrates, you're lucky, by the way. Sometimes you are not that lucky and you can absorb, and because of the energy it can break chemical bonds in your cells and so on, so it can cause mutation. It's not very safe, so we would like to detect radiation in the nature. So that's the topic we're gonna talk about. And this is one count. I don't know exactly how to spell, but Geiger counter. It's a gas-filled tube. When you have a nuclear particle, radioactive particle, it excites the gas, and because of the high voltage, whenever you have any ion or like charged particle, because of the excitation, it will be transferred to anode or cathode. Then you will have some current and you can sense the particle. And in a similar way, you can take the incoming particle and it can excite some photon, and you can use photomultiplier tube. So you call it scintillator. And then you use photomultiplier tube to increase the number of photons, the electrons. So this photon excites electron. So here you are trying to convert the incoming particle as an electron. Then you multiply this electrons from one to many. Then you can read it. In early days, people use this cloud chamber. If you have a kind of cold gas condensed in some medium, and when a particle passes, you can see some bubbles form in that cloud. So in the nuclear research, people also use much more sophisticated detection methods. So this is, for example, one example. So to quantify this radiation, and when we measure, this is how we quantify. When we have 1 disintegration per second, we call it 1 becquerel. And if you, at the time of the Curie, they quantify as when you have a 3.7 10 to 10 disintegration per second, they call it 1 Curie. Probably this is a kind of one of the elements, I'm not sure which one, but rhodium or palladium or something, some certain mass of this nuclear element has this much disintegration, and they define this unit. But later, to make it easy, we call it 1 disintegration per second as a 1 becquerel. Half-life and rate of decay. So nuclear decay is a random process. The decay of any nucleus is not influenced by the decay of any other. So which means that this is not the case for the atomic bomb. Actually, you have a stimulus decay in the atomic bomb. We are talking about normal, like this, the radioactivity in nature and some element in the rest state. Because the radioactivity happens in nucleus, the other elements or the atoms, actually they don't influence the other. The nucleus is they don't influence each other that much, because being very very small at the center of atom. So because of that, it's a random process, and as you have more material, you have more decay, and we call it this decay rate. And it depends also we call this half-life, and the decay rate, the number of decay is going to be proportional with the number of nuclei, because if you have a more nuclei, you will have more disintegration or radioactive process. You have a decay rate of decay, and of course it depends on how long you wait. And usually we call this we have this half-life term when a number of element decays its half of it at a certain time, and it's constant. And the half-life time is given by logarithmic 2 divided by decay rate, and logarithmic 2 is 0.693 divided by lambda. So if you have a faster decay, which means that the alpha is larger but the half-life is going to be shorter. So this formula actually can be integrated, this decay formula, and it will be n number of particle or the nuclei at certain time. It's given by the initial number of nuclei exponential times minus lambda times t at t0. E to the 0 is going to be 1, and n equals n naught. When the t equals half-life, so ln2 divided by lambda ln2 divided by lambda. So you see the lambdas are gonna cancel. E to the minus ln minus ln2, sorry. Then the minus sign goes to the 1 over 2 in the logarithmic exponential ln 1 over 2. Then these are gonna cancel, exponential and logarithmic. Then what you have is 1 over 2, and at this time n is gonna be n naught times 1 over 2. Then that's the half-life. So for example, let's say you have a 10,000 particle at time 0, and in the first half-life now you have 500, in the second one you have 250, in the third one you have 125, in the fourth one 62.5, and so on. So as you see, when you have less and less particle, you lose less and less amount of particle. This is one problem about nuclear radioactive decays. you have alpha, beta, and gamma rays. The question asks, can you define which one, 1, 2, 3? Can you find the correspondence between 1, 2, 3 and alpha, beta, and gamma rays? So 2, you can pause and then solve by yourself. So 2 is not affected by magnetic field, right? So because of this, 2 is gamma particle, and you have 1 and 3. Without doing any right hand rule, you can actually tell the difference. Alpha particle is much heavier compared to the beta particle or electron. So a magnetic field is gonna be able to bend the beta particle much stronger, the smaller curve, but alpha particle deflection is much less because of being heavier. Okay, another question. A system consists of n not radioactive nuclei at time 0. The number of nuclei remaining after a half-life, which means that 1 over 2 T half is A quarter, B 3 divided by 4, C is n not divided by square root of 2. So you can pause. Okay, actually this we can do with the math or without math. N not at half-life. Now you have n over 2. Here you have n over n not divided by 4. So you have such decay. So question asks how many nuclei at half of the half-life at this. So this is not true, right? It means this is 2, 1, and 3 divided by 4, and 1 quarter, 1 over square root of 2. So as you see, this is n over 2, and if you come this point, this is at the middle, and this is n not divided by 4. But as you see, this happens much earlier because of this is not linear, so this is exponential decay. Okay, so actually at this point you should have less nuclei. If it was linear, then you can tell it's gonna be 3 over 4, but this is not linear. This amount is reached much earlier than half of the half-life, and the answer is gonna be square root of 2. But if you want to calculate how you can do it, let's say you have n, you're trying to find n, you have n naught exponential life decay rate and time, right? So in the half-life, okay, so you can do it in 2 ways. Actually, let's do the classic way. So you have n naught exponential minus lambda. Let's describe in terms of half-life. Lambda is ln2 divided by half-life, ln2 divided by half-life, and time is half of half-life. So you see you can cancel the half-lives, and you have n equals n naught exponential minus ln2 divided by 2. Then so you can calculate this with your calculator, or you can do this in the logarithmic. Minus sign means the division in the inside, and the division means the square root. So exponential and logarithmic cancels. You have n naught divided by square root of 2. Okay, so this is how you can solve this problem. Again, you can use two ways. I mean, the A is not possible. B is the answer if you have a linear decay, but this is an exponential decay, so B is not option 2 either, and the only left is C. Or you can use this formula to find the exact answer. So radioactive dating can be done by analyzing the fraction of carbon in organic material. I read it's carbon 13. This is 14. Let me double check this later on, so you can check. I always thought it's a carbon 13, but in the lecture note it says carbon 14. Anyway, it doesn't matter that much, but so this is how we can use the radioactive dating in biological samples. So when the plant dies, okay, let's go back. In the nature, we have carbon 12 and carbon 14. During the living process, you always exchange the carbon within nature, in the atmosphere and environment. So your carbon ratio is equal to what's the default in the atmosphere and the nature, okay? But when you die, or any organic living creature, living plant or animal, when it dies, it stops exchanging the carbon, and its carbon starts to decay, 14. And later on, when you find a fossil, let's say you measure the ratio between carbon 13, carbon 12 and 14, then you can compare with what's the reference ratio in the nature and atmosphere. Then you can find the age of it. For example, when the object is older than 60,000 years, it's not easy to do. But maybe this is an old slide, or from the textbook. Nowadays, I think people can use more, because we have more sensitive measurement methods or instruments. We can date older objects than 60,000 years. For like the billion, 10 to the 9 years, to, let's say, for for the scales, let's say in the billion years, we use uranium. So for example, for Earth's rocks, we can use this uranium to date. Okay, this is one problem. When a stationary uranium-238 nucleus decay into the 234 thorium with an alpha particle decay, is the kinetic energy of alpha particle greater than, less than, or the same as the kinetic energy of thorium? So you have a uranium 238, and it goes into the alpha decay. And becomes alpha and thorium. For 2 proton and 2 neutron. So it's a stationary, and they have to conserve the momentum. One must go to left, other one goes to right. So it asks the kinetic energy of alpha particle is greater, less than, or same energy of the thorium. So you can pause, solve by yourself. Okay, how are you gonna approach this problem? Now you need to think of right now what you need to know is the momentum is conserved in this case. So energy is conserved too, but when now we don't know how much mass is lost, so we don't know exactly how much energy they have. But what we can do is, when they have the same momentum, it's called P alpha and P thorium, these are momentums, then they must be equal. And then kinetic energy of alpha particle is going to be kinetic square root of momentum divided by 2m alpha. And for the thorium, square root of the momentum divided by 2 times mass of thorium. So how you can, if you don't know how to drive this, mv square is the kinetic energy of a particle or the mass. The momentum is mv, right? So if you write for the, let's say for the velocity, if you write p divided by m, p square m square. So you have one mass here, and you have 2 mass in the denominator, m square, you have p square divided by m. So if the momentums are the same, then what we need to compare is the masses. But you see that the mass is the denominator, and it's inversely proportional. It means, so if the mass of the particle, alpha particle, is less, so the kinetic energy will be larger, and the thorium mass is much more because it has 234 nucleon. So the kinetic energy of thorium will be less compared to alpha particle. So let's pause here and then continue in the second video. We will solve practice questions about the nuclear physics.